All right, recording is rolling. It is Tuesday, April 16. Today's going to be a video day, more or less. I gave you guys this quarter page. Does anybody not have this quarter page? Right. So on one side says dark matter, although it's really going to be on dark matter and dark energy. This is one of my favorite TED Talks. Patricia Burchett tell you about that. Right? On the opposite side is, you guys might be familiar with a YouTube channel, a guy named Mark Rober. He used to be an engineer for NASA. Now he has this little YouTube channel. And so tell you guys a little bit about NASA. Big reason I'm showing you guys is because there's a Sunshine State Standard I have to tell you guys about why NASA is awesome, and he has a really good synopsis in about under 10 minutes. So we go there, right? Now, before I roll these, I do want to set up a little bit about this TED Talk on, actually, the dark energy section is what this can be related to. And so if you ask the question like, what is the size of the universe, what's happening to the size of the universe as time goes forward, right? Let's say like, what is the size of the universe as a function of time, right? So time's ticking along, what's happening to the size of the universe, right? Now, if you go back to, let's say early Einstein days, around 1900, right, turn of the century, over 100 years ago, people naturally assumed a static size universe, right? If you look at the stars in the sky, say, okay, they look like they're pretty much just kind of staying there. Right? Maybe everything's just kind of like where it is, right? So that's here. I'll just draw like a pink line. It's like it's basically assuming like a flat line, right? So time ticks forward, but the size of the universe doesn't change. And if you think about that for a little bit, I don't even know exactly why they would have necessarily assumed that would have been the case, because it didn't even really quite make sense from a gravitational point of view, right? Think if all masses are gravitationally attracting, if you started off with something like that, then after some time, everything's just going to pull together. So it should like go down like some big crunch. Everything should just like crunch together, right? Maybe form some giant black hole or something, right? But anyway, that's what people started assuming. Now, back in the 1920s, this guy named Edwin Hubble, who the Hubble telescope is now named after, was making astronomical observations and noticed that almost all galaxies relative to us appear to be redshifted. You guys remember redshift and blueshift? It's the Doppler effect, but applied to light, right? So you guys remember Doppler shift, right? If you're standing by the side of the road, say you're on the sidewalk, car goes by, something, you hear pitch shift. Now it's a sound version of Doppler shift, but light is similar to that, right? So you guys remember like red wavelengths of light is like long wavelengths, and then Roy G. Biv, when you get to violet, that's like shorter wavelengths, right? And that's just the visible spectrum, right? That's even part of the larger electromagnetic spectrum, right? There's different parts of that, right? Right. So anyway, you see most galaxies relative to us are red shifted, which means the light's been stretched out, which indicates that they're moving away from us really fast. In fact, you can also say the further away galaxies are from us, the more they're red shifted. Okay. There are I think a few exceptions. I know Andromeda Galaxy is blue shifted compared to us, which means it's headed towards us. The Milky Way and Andromeda are eventually going to collide, but almost all galaxies are redshifted, and the further away they are, the more redshifted they are, right? So then the question is, okay, well, now we know the universe is not static, so what is it doing, right? And there were three main hypotheses that were thrown around for the rest of the 20th century, right? And I'll throw them here, right? So one hypothesis is, well, you could run the clock backward. Say, I see everything's moving away from us. What if you run the clock backward? And it looks like everything was about same place, same time, approximately 14 billion years ago, plus or minus a little bit, right? Which was the first idea of a Big Bang theory. Now, since then, there's been more evidence for this Big Bang, right? But this was like the first idea. It's like, hey, if you see everything's moving away from us, and you run the clock backward, right? Sure, that everything was the same place, same time, 1 point. So about 14 billion years ago, let's say there's this Big Bang. But see, everything is gravitationally attracting. So maybe kind of like if you throw a ball straight up in the air and then eventually it's going to come back down, right? Well, maybe that's kind of like what the size of the universe versus time would be, right? So that's our first hypothesis thrown on the board, right? And then, okay, there's some evidence for that. I should throw in the detail too that there is no such thing as the center of the universe. So in this Big Bang model, it's not like everything's exploding away from a single point. It's like the center of the universe is like everywhere. And no matter where you are in the universe, you could be on the Milky Way galaxy or pick any random galaxy, everything's moving away from that point, right? So expansion is universal. There is no center, right? It's part of this model, right? Right. Now, you could have this, or you could look at this and say, well, hang on, if I'm thinking about that throwing a baseball in the air analogy, you could throw a baseball so fast upward that its escape velocity and just runs away from the Earth forever. So in that case, it would be slowing down after, like, for the first few miles after you throw it up, because Earth is pulling down on it, right? But maybe has enough juice, enough speed, reach escape speed, it's going to fly away, right? And then the size of the universe versus time, the sort of analogous idea to that is maybe something like this, right? Where, yeah, the gravitational attraction between all the galaxies is, yeah, pulling together, right? So it's like a concave down curve, right? Kind of like this one's concave down. These are all concave down, right? But maybe the Big Bang 14 billion years ago, there was enough bang that everything's going to race away from each other. Okay, then you can look at that and say, well, hold on, actually, there is maybe a third possibility too, which is kind of analogous to what if you throw a baseball at just the right speed, just the right angle, that it starts orbiting the Earth. Okay, that would be kind of analogous to what if the universe reaches an asymptotic size. Right, so go back 14 billion years ago. What if the bang was just so that all the galaxies are gravitationally attracting, right? But the universe is going to sort of reach an asymptotic size, maybe something like that. Right. So we're done with the static universe. We know that's not the case. I'll X that one out. Right? The universe is definitely not static size. Right? So we got some kind of dynamic universe, but which of those three curves are we on? Right. So for like most of the 20th century, right, those three hypotheses are being thrown around. Nobody really knows. Okay. And then near the end of the 20th century, beginning of 21st century, it's about 20-some years ago relative to us, different teams of scientists, different teams of astronomers around the world set out to answer this question of which one of these three curves are we actually on? And they all came to the same conclusion, which was none of the above. There's actually a fourth option that nobody was even really considering that ends up being the answer to this question. All right, so yeah, with that, again, what I'm hinting at is something that eventually becomes termed dark energy. So I'm going to flip my screen over here. All right, you guys ready to fill out that quarter page? Right, you're all on the side. It says Patricia Bertrand. It says dark matter. She talks about dark matter, and then she talks about dark energy. All right, we're going to switch over, do that. You guys follow along, and then should be good points for today.